All right, today we are going to be reading pages 108 to 113, Ocean Water Chemistry. Just like we talked about what was in the air in terms of in dry air, we had oxygen, nitrogen, carbon dioxide, argon, and other gases. We're going to talk about what the makeup is of ocean water. And I'm sure that you all know that there's going to be water and there's going to be salt. And we're going to talk about the different kinds of salts. Here we go. Page 108. If you've ever swallowed some water while you were swimming in the ocean, you know that the ocean is salty. Why? Well, according to an old Swedish legend, it's because of a magic mill. This mill could grind out anything its owner wanted, such as herring, porridge, or even gold. But a greedy sea captain once stole the mill and took it away on his ship, but without finding out how to use it. He asked the mill to grind some salt, but then he couldn't stop it. The mill ground more and more salt until the captain's ship sank from its weight. And according to the tale, the mill is still at the bottom of the sea grinding out salt. Obviously, not a true story, but the salty ocean. Probably no one ever took this legend seriously, even when it was first told. The scientific explanation for the ocean's saltiness begins with the early stages of Earth's history, when the ocean covered much of the surface of the planet. Undersea volcanoes would erupt, spewing chemicals into the water, and gradually the lava from those volcanic eruptions built up the areas of land. Rain began to fall on that bare land, washing more chemicals or elements of salt like substances and washing more of that stuff from the rocks into the oceans. Over time, those dissolved substances built up to the levels present in the ocean today. The salinity. Just how salty is the ocean? If you boiled a kilogram of ocean water in a pot, that's 1,000 grams or a liter, basically. If you boiled a kilogram of ocean water in a pot until all the water was gone, there would be about 35 grams of salt left in that pot. So a kilogram is 1,000 grams. So you're thinking of it would be roughly the same as a liter. So if you took a liter bottle of salt water and you boiled it away, you'd still have 35 grams of salt left. On average, 1 kilogram of ocean water contains about 35 grams of salts. So we say it is 35 parts per thousand because a kilogram is 1,000 grams. This total amount of dissolved salt in a sample of water is what we call the salinity of that sample. Some water has more than 35 parts per thousand, so it has a higher salinity, and some ocean water, some water has less salt than that, and it has a lower salinity. The substance that you know as table salt, what we eat, sodium chloride, is the salt that is actually present in the greatest amount in ocean water. So when you hear sea salt, that's exactly what we're talking about when you have that on your table. When sodium chloride dissolves in the water, it separates into sodium and chloride particles called ions. There are other salts, such as magnesium chloride, and they form ions in the water as well. And so basically, what happens is I'm going to draw a little um, picture for you is that you have sodium chloride and its chemical formula is NaCl. And you see I put a plus and a minus. When you put that in dissolved water, okay, what you're going to have in that water is you're going to have obviously the water molecules. And you'll see I sort of have like an H2O there, but you'll get that Na molecule and that Cl molecule, and they will sort of break apart. And so you'll have these sodium and chlorine ions that will bond to other things in the water. Okay, so I'm gonna start here again. It says, the substance that you know as table salt, sodium chloride, is the salt present in the greatest amount in ocean water. When sodium chloride dissolves in water, it separates into sodium and chloride particles called ions. And an ion means it has a charge. So the sodium would be a positive and the chlorine would be a negative charge. Other salts, such as magnesium chloride, form ions in the water in the same way. Together, chloride and sodium make up almost 86% of the ions dissolved in ocean water. So that table salt, that sodium chloride, those two elements together are about 86% of the salts in the water, is what we're saying. Ocean water also contains smaller amounts of about a dozen other ions, including magnesium and calcium and other substances that organisms such as us need, such as nitrogen and phosphorus. Okay, so you can see here the sodium and the chloride together, and they have a little table salt shaker here, together is about 85%, 86 almost percent of the salt in the ocean. But there's also sulfates, there's magnesium chloride, there's calcium chloride, there's potassium chloride, and those are other kinds of salt. Okay, we'll keep going. So salinity and density. I think that's it there. Okay. So here you see these people are actually floating. They're in an area called the Dead Sea. As you can see, these people are relaxing with the paper while floating in the water. The Dead Sea in Israel is so salty that people float much easier. So it has a much higher salinity. Regular ocean water, remember, is about 35 parts per thousand, and the Dead Sea has a higher salinity. And so, what makes the different variations in salinity? We're going to read about that. In most parts of the ocean, the salinity is between 34 and 37 parts per thousand. So that 35 is sort of an average. But near the ocean surface, we have fresh water being added. It says near the ocean surface, rain, snow, and melting ice add fresh water that lowers the salinity. So the surface is slightly lower. Salinity can also be lower near the mouth of a large river, such as the Amazon or Mississippi, because that's fresh water leading into it. These rivers empty great amounts of fresh water into the ocean. Evaporation, on the other hand, increases salinity since the salt is left behind as the water evaporates. So in the Dead Sea, it's a very hot area and they don't get a lot of rainfall. So you have a lot more evaporation happening with that salt being left behind. So the Dead Sea, where those people are reading the paper, has a higher salinity. For example, in the Red Sea, where the climate is hot and dry, the salinity can be high as 41 parts per thousand. Salinity can also be higher near the poles because as the surface water freezes at the poles, that salt is left behind in the remaining water. So when the water freezes at the poles, creating icebergs and glaciers, that the salt doesn't freeze as part of it. And we've talked about how before why we use salt on the road because it lowers when we did our hail lab, we talked about how salt lowers the freezing point. And so if the salt doesn't freeze, but the water, the fresh water itself will. Effects of salinity. It says salinity affects several properties of ocean water. For instance, ocean water doesn't freeze until the temperature drops to about negative, that's my dog over there, negative 1.9 degrees Celsius, because we talked about how salt lowers the freezing point. So it has to actually get colder than zero for the ocean water at the poles to freeze. The salt acts as kind of an antifreeze by interfering with the formation of ice crystals. Salt water also has a higher density than fresh water. There, because of those ions filling in the spaces between the water molecules, it's more dense. You can fit more molecules in the same amount of space. That means that the mass of 1 liter of salt water is greater than the mass of 1 liter of fresh water. Because its density is greater, seawater has a greater buoyancy. It lifts or buoys up less dense objects floating in it. That is why an egg floats higher in salt water than in fresh water, and why the people in figure 14 float so effortlessly in the Dead Sea. If you went home and you were to take a raw egg and you put it in a cup of water, you'll notice that egg would sink to the bottom. But if you added a tablespoon of salt and stirred gently, not cracking the egg, and you continue to add salt, you'll notice that eventually you could get that egg to float in the middle of the cup. And if you continue to add salt and stir gently and get that, you could actually get the egg to float at the top of the water as well. Because as you add the salt, you are increasing the density of the water. And so when you have fresh water, the fresh water is less dense than the egg. When you're adding the salt, you make that salt water more dense, and then you get to a point where the salt water is more dense than the egg, and the egg floats. If you guys remember how density works, less dense substances float. Other ocean properties. In New England, the news reports on New Year's Day often feature the shivering members of a polar bear club taking a dip in the icy Atlantic Ocean. Yet on the same day, people enjoy the warm water of a Puerto Rico beach. Like temperatures on land, temperatures at the surface of the ocean vary with location and the season, and gases in the ocean water vary as well. So you know that the areas near the equator are always going to be warm, and areas near the poles are always going to be cold. And then you have seasonal changes in specific areas as well. Temperatures of ocean water. Why do surface temperatures in the ocean vary from place to place? The broad surface of the ocean absorbs energy from the sun. Near the equator, the surface ocean temperature often reaches about 25 degrees Celsius, which is about room temperature. But as you travel further away, the temperature drops the temperature drops as you travel away from the equator. Because warm water is less dense than cold water, warm water forms only a thin layer on the ocean surface. Generally, the deeper that you ascend into the ocean, or the deeper you go, the deeper you descend, the colder and more dense the water becomes. When the water temperature is lower, the water molecules stay close together than at higher temperatures. So if you take a sample of cold water, it's going to be a greater density than warm water. And we've talked about that with air. We said if you heat air, air will be expand and become less dense, and if you chill air, it will become more dense and colder and more dense. Um, Air molecules move a much greater amount than liquid molecules will. So while that you can see it very obviously with gases, with a balloon going outside in the winter, that if you take a helium balloon outside in the winter, you can see it shrink, and if you bring it in, you can see it expand. You don't notice it as much with liquids because it doesn't do it that as it's not as great of a change, but it is absolutely a change, and it is actually incredibly important for the turning over of our water. So going back here, because warm water is less dense than cold water, warm water forms only a thin layer on the ocean surface. Generally, the deeper you descend into the ocean, the colder and denser the water becomes. When the water temperature is lower, the water molecules stay closer together than at higher temperatures. So a sample of cold water has more molecules than a sample of warm water of the same volume. The sample of cold water is denser. Gases in ocean water. Just as land organisms use gases found in air, ocean organisms use gases found in ocean water. And believe it or not, there are gases in the ocean water. You might not think of it. They are dissolved gases. Two gases that ocean organisms use are carbon dioxide and oxygen. There's carbon dioxide and oxygen dissolved in the ocean water. Carbon dioxide is about 60 times as plentiful in the ocean as it is in the air. So if you were to take a sample of water and of ocean water and a sample of air about the same size, there would be 60 times more carbon dioxide there dissolved, believe it or not. The algae and the plants in the ocean, they need that carbon dioxide for photosynthesis. And other animals, such as corals, like the coral reef, also use carbon dioxide, which provides the carbon to build their hard skeletons. Unlike carbon dioxide, though, oxygen is scarcer or less present in seawater than in air. Oxygen is most plentiful in seawater near the surface, obviously, because it's closer to the surface. It's getting that oxygen interacting with the surface. And in deeper ocean water, you're not getting that. Oxygen in seawater comes from the air and from the algae in the ocean. So, as plants use carbon dioxide to turn into food, it gives off oxygen. So, the oxygen in the ocean comes from the surface and it comes from those plants that are in the ocean. So, oxygen in seawater comes from the air and from algae in the oceans as a product of photosynthesis. The amount of oxygen in seawater is affected by the water temperature. The cold water in the polar regions actually contain more oxygen than warm tropical waters, but there is still enough oxygen in tropical seas to support a variety of organisms. And it's really important. We need the carbon dioxide in the oceans, obviously, for plants, but we also need that oxygen for fish and other organisms that require it. So here's a picture of the water column. We're going to be doing something like this in our packets, but you'll see here that this is a scuba diver with a tank on. That a scuba diver can descend to about 40 meters or about 120 feet below the surface of the earth before it becomes dangerous. There are different zones in the ocean, and so as we go from the top of the ocean to the top of the ocean zone is called the surface zone, which makes sense. It's at the surface, and it only goes to about 200 kilometers below the surface. And that's the area that's going to have the most variation in temperature because it's going to be warmer near the equator and colder near the poles. You're going to get a lot more variation in salinity because if you have an area where there's a lot of evaporation, you'll have higher salinity. And if you're near the ocean, if you're getting a lot of rain, or if you're near the mouth of a river, you'll have lower salinity. That the surface zone is getting the most amount of daylight, so you'll have the most amount of plants there. And you can see the surface zone extends from the surface to about 200 meters, and the average temperature is about 17.5 degrees Celsius. But again, we can get up to 25 degrees and we can get, to freezing temperatures. Okay. The color and the light, it says the sun penetrates the surface of the ocean. It appears first yellowish, and then as you go deeper, then blue-green as the water absorbs the red light. No light reaches below about 200 meters. So below the surface zone, there's actually no surface light penetrating that surface. Okay, the next zone would be the transition zone, and that extends from the bottom of the surface zone to about 200 meters to about 1 kilometer. So 200 meters to 1,000 meters. And from the 17.5 degrees average, it drops very quickly to about 4 degrees Celsius. It's very, very cold. And you can see the temperature near the surface, the temperature is affected by the weather above. In the transition zone, however, the temperature just drops rapidly. And by the time you get to the deep zone, which we're going to talk about, it's always extremely cold. Now, the deep zone is anything below 1 kilometer. So anything deeper than that, there's absolutely no light. The temperature is pretty standard. It's about 3.5 degrees, very, very cold, and the salinity remains pretty constant. Now, the salinity, like we talked about here, it says the rainfall decreases the salinity near the surface. So that surface zone is going to have variations, while evaporation increases salinity in warm, dry areas. Below the surface zone, though, salinity remains fairly constant throughout the water column. So the transition zone and the deep zone both have a pretty constant salinity. It's not changing like it might be at the surface. And then, of course, as you get below the surface, you're going to have a constant salinity, or but you're still gonna we're gonna talk about the density of the water. The density is gonna be the water is very cold there, so it's gonna be more dense in that capacity. It says the density of seawater depends on the temperature and salinity. The ocean is generally least dense in the surface zone, and it's more dense in the deep zone. It's less dense in the surface zone where it is the warmest. However, higher salinity also increases density. The most dense water is found in the cold, deep zone. And then pressure, as I'm sure you can imagine, that we cannot descend to the bottom of the ocean because of the amount of pressure from. We talked about how we have air pressure with the air column. Now, air is can be pretty dense if we're talking about the amount of air. But if you're thinking about water is far more dense than air. So if you can imagine the turn the air column into a column of water above you as if you were in the bottom of the ocean, and that pressure is pretty it can crush you, and we don't even have the technology or tools or equipment where we can really get to the bottom of the ocean because there is so much pressure that we don't have materials that can currently withstand that right now. So density, pressure, excuse me, the pressure increases at the rate of 10 times the air pressure at sea level per 100 meters. And you can see that there. So we do have these two, what we call submersibles that you're seeing here. This is called the submersible, and it can descend to about 4 kilometers. Again, that pressure is pretty intense. And then this is called the Trieste. It dove to the record of 11 kilometers, and then they started to hear cracking, and so they had to abandon their mission and they had to come back to the surface because obviously if there was something because there were people in there, if something would have happened, those people obviously would not have survived the ascension to the surface. So again, looking at these different zones, we have the surface zone, the transition zone, and the deep zone, and we're going to be talking about how color and light, temperature, salinity, density, and pressure change as you continue to go into the water column. Okay. Changes with depth, we've sort of touched on all these things. We're going to summarize them here. If you could descend from the ocean surface to the ocean floor, you would pass through a vertical section of the ocean referred to as the water column. Figure 16 that we just looked at shows some of the dramatic changes you would observe. Decreasing temperature. As you descend through the ocean, the water temperature decreases. There are 3 temperature zones in the water column. The surface zone is the warmest. It typically extends from the surface to 100 and 500 meters, depending where. Okay. Then you have the transition zone, and it extends from the bottom of the surface zone, wherever that might be, to about 1 kilometer. And the temperatures drop very quickly as you go from the surface zone through the transition zone. It gets to about 4 degrees Celsius. Below the transition zone, as we stated, is the deep zone, and the average temperature there is about 3.5 degrees Celsius in most of the ocean. And then as you descend, the pressure increases. The water pressure is the force exerted by the weight of the water. Pressure increases continuously within depths of the ocean. Because of the high pressure in the deep ocean, divers can only descend to about 40 meters. To observe the deep ocean, scientists must use a submersible, an underwater vehicle built of materials that can resist pressure. We have one more section of this we'll be reading. I hope this made the reading easier to understand and the explanations helped as well. Bye.